Hello, ladies and gentlemen. I hope you're all doing well. We're looking at question B3 now on our 2018 Canadian Senior paper. This is the last question on the paper, usually the hardest question. But, A6 can be hard depending on what the topics are for the questions, but usually B3, you want to save a bunch of time for that. A string of length n is a sequence of n characters from a specified set. For example, BCAAB is a string of length 5 with characters from the set ABC. A substring of a given string is a string of characters that occur consecutively and in order in the given string. For example, CA is a substring of BCAAB because CA is there, but BA is not, because no matter where I look, I can't see BA together. Sure, we've got AB, but it has to be in this order. All right, looks like we've got 3 parts. Yeah, 3 parts. Okay, A. Let all strings of length 4 with characters from the set, list all strings of length 4 with characters from the set ABC in which both the strings AB and BA occur as substrings. For example, ABAC should appear on your list because it's got both an AB and a BA. Alright, well, they're strings of length 4. And at least in their example, they show how the AB and BA can merge in a sense. So I have a feeling we're going to be dealing with some cases here. But let's take a look, see. So we do need to explain everything, so suppose these appear separately. Well, either you'll have AB followed by BA, or BA followed by AB. It doesn't matter the particular order. But we only have 4 characters to deal with, so if these things are really separate, they do have to appear in some order. Now instead, suppose we have AB and then A, which is the one that they suggest. It can appear, let's say, starting in the first or second position. A, B, A, and then we'll have another character, or we have a first character and then A, B, A. Alright, so what could we have? Well, we could have an A here. Or a B could be the other one. Oops. Or a C. Now I think these 2 that I've just written are going to appear on the next thing I write, but we will find out in a moment. Because they've got BAB, which is my last case. So either the AB and the BA are separate, they are merged with the AB first, or they are merged with the BA first. So we have the BAB first. Either it can appear in the first 3 or the last 3 spots. So we can have A's. Or we can have B's in those spots. Or we can have C's. But those are the only characters we're allowed to use. And that's it. Now, the one that they give me, it was CBAB, wasn't it? ABAC. So we should have that. Yeah, that's the one they gave me. But you'll notice this one here and this one here are duplicated. So we can ignore them. So what can we have? We could have ABBA, AB, because they want us to list them out, ABAA, AABA. We just want to make sure we don't accidentally have the same thing twice, because I imagine there might be a mark off for that, for not realizing. So it looks like there's 12 of them. So there's our answer. There we go. Alright, so those are my 12 responses for part A. I think we're quite clear in how we explained how we got them. Now B part. Determine the number of strings of length 7, so a bit longer, we might not be able to list them out, with characters from the set ABC, in which CC occurs as a substring. Okay. So I can think of two ways to maybe approach this. We could say, all right, let's have some CCs. How many CCs in a row can you have? Well, how many CCs, period? Because, I mean, if we had all 7 Cs, that would count. CC appears lots of times, 6 times in that. So we could try and count CCs and ask where can I place my various CCs and try and add things up there. I think that's going to be a bit too much variation. So instead, I think, and this is a common counting technique, when you find that the thing that you want to count is difficult or has too many cases, try counting the opposite and subtracting that from the total. And it's very easy to see that if you've got 7 characters in your string and 3 choices of letter, we're going to have 3 to the 7 possible strings, period. What we want to do out of that total list is remove the ones that don't have CC. And that might be easier to count, and I think that'll probably have less cases. Because I think one of the things that's going to be hard to count up if we're trying to just say, well, how many CC substrings can I have and where can they be? I think that'll be hard because the CCs can overlap. 3 Cs in a row is technically 2 occurrences of the substring CC, and I think that might be a little harder to count. So I'm going to say, okay, 3 to the 7 minus... Now, if this turns out to be difficult, I will try the other way, and if that turns out to be difficult, I will try something else. Okay, but let's say... Notice there are 3 to the 7 substrings in total. I don't think... I mean, you could explain it by saying each character, there's 3 possibilities. I think it's fair to just say 3 to the 7 and move on without having to say too much about it. Or not substrings, strings, I guess. Okay. So how can I avoid having CC? Well, if I've got no Cs, so probably it's a good idea to usually tell them what you're planning on doing. Let us instead count number of strings without CC. Now, if I had 0 Cs, so this would be a case 0 Cs, then really you get 2 to the 7 possibility. Just using A's and B's, each character has 2 choices. If you only use A's and B's, you're not going to have any C's at all. Now, if you've got 1 C, 1 C, where can that C go? Well, it doesn't really matter where it goes, right? Because it's going to be the only C. Now, when we get to 2 C's, we're going to have to make sure that they are apart from each other. But with just 1 C, and you probably want to explain this, 7 choices where to put C, and then 2 to the 6 possible ways. Because once I've got a C, then either it's an A and a B here, or an A or a B here. 2 choices everywhere else. So 2 to the 6 possible ways to pick the other letters. So how many are there with just 1 C? 7 times 2 to the 6. So in total so far, I've got 2 to the 7 plus 7 times 2 to the 6. We could work these out. I mean, 3 to the 7 is going to be 2187. We might do that at the end. We'll see. Now here's where things might get a little harder. So let's see. Suppose we've got 2 C's. We don't want them placed together. They cannot appear together. Is there a quick way to count that? Well, where can I place the first C? The first C can go in any one of these spots. It can't go in the last spot because if it's the first C I read from left to right, it would have to go here, and then the next one would have to go here. And then I'd have CC as a substring. So the first C could be placed in the first 5. Now, if I place a C here, I can't place a C here. I've got 5 choices for where to place the next C. If my first C is here, I can't place a C here. I've got 4 choices where to place the next C. Here, 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 or here. And this keeps going. 3 choices of where to put the next C. 2, and finally, you just can't. You'd have C something and C at the end, and that would be one way. So in total, 15 ways to choose where the C goes. So 15 times 2 to the 5 ways to fill out the other ones. And you can explain that just as you explained the 2 to the 6 that we used. But it's count the number of ways to place the C's and then fill in the rest with A's and B's. That's the basic idea here. All right, 3 C's. I think 3 C's might be the hardest one of all, because I think 4 C's, if it's 7 of them, it's just going to alternate, and I don't think you can have more than... You can't have 5, because then you'll have to double up. Will the same sort of method work? We want to place the C's, so where could our first C be? Well, we can have a C here, then you can't have a C here, and then where can the next C go? Oh, this is getting trickier. Not impossible, but certainly trickier. You do some subcases. We could have a C here, and then no C there, and then you'd get 3 possible choices. Or my next C could go here, and then I'd have 2 possible choices, or my next C could go here, and I'd have 1 possible choice. So in total, I've got 6 ways to pick the C's if the first thing is a C. Looks like we're getting some triangular numbers. I'd explore, maybe we'll need this in part C, but it definitely looks like we're getting some triangular numbers here. I think we could probably just continue on. So if I put a C in the second, if that's the first C that occurs from left to right, then, well, I suppose we could have a C here, and then you'd have 2 choices. Or a C could appear in this spot, and then can't have a C here. Excuse me. And I guess you could have you'd have to have your C here. So only 1 possibility. So there's 3. I suspect the next one will be the last that we have to deal with. You could have C, nothing, and then you'd have to fill it in C, nothing, or C, an A or a B, C, an A or a B, C. Only 1 way there. 6 plus 3 plus 1 is 10. Just briefly, if I had a C here, I could put my next C here, except that's not allowed. So it'd have to go here, and then the last C would have to go here, and that's not allowed. So 10 different places to put these 3 C's, and 4 choices for what the other letters are, or 2 choices for each of the 4 other letters, I guess is the way to say it. Okay. But I think it's it might be a good idea at some point, if we need it for C part, to investigate how many ways can I place, 3 C's. I haven't read the C part, so I don't know if it's going to be talking about CCs or anything like that. But it's interesting. Looks like if I've got 2 C's, I get triangular numbers. If I have 3 C's, it looks like it's a sum of triangular numbers. Maybe with 4 C's, if we had more space, it would be a sum of sums of triangular numbers. That'd be interesting. It'd be interesting to get formulas for that. Anyway, we've got 1 more case to go. 4 C's, but how do I know it's the last case? Because there's only 1 way to do this. There we go, 4 C's. So, I'd probably point that out only 1 way. Last case, that sort of a thing. But there's 1 way to do this, and then 2 to the 3 ways to fill in the other choices. And if you had 5 C's, 6 C's, 7 C's, that's too many. Remember, we're trying to avoid having 2 C's in a row, or 3 C's in a row, or any number of C's in a row. So, number of strings with CC as a substring is going to be 3 to the 7 minus 2 to the 7 with 0 C's, minus 7 times 2 to the 6, minus 15 times 2 to the 5, minus 10 times 2 to the 4, minus 1 times 2 to the 3. And there was technically only one way to get no C's in there, just to complete the sort of pattern we've got. I'm just going to double check my numbers. Everything looks good. So we'll just grab a calculator, work this out. 3 to the power of 7, 2187. 2 to the 7 is going to be 128. 2 to the power of 6 is 64 times 7, 448. 15 times 32, 480. 10 times 16, well, that's going to be 160. And then minus 8. So 2187 minus 128 minus 448 minus 480 minus 160 minus 8. 963 different possibilities. So there we go. That's not the nicest looking number. It's a multiple of 9, but I'm happy with the way we did it. It would be worth perhaps exploring the other way, count the different ways you can place CC. But I think with all the overlaps that could be possible, it might not be the nicest thing to work out. But I don't know. If you want to try that out, let me know how it works. If it's faster, slower, easier to understand, please let me know down in the comments below. But I think I'm going to move on to C part to finish off the contest. Get ourselves a little bit of space. And then what have we got here? Let f of n be the number of strings of length n with characters from the set A, B, C, so that the following happens. Is this going to be a combination of A and B, I think? CC occurs as a substring. Okay. Similar to the last one. And if A, B, or B, A occurs, they might not need to, but if A, B, or B, A occurs as a substring, then there is an occurrence of the substring CC to its left. So, for example, if I've got an AB at some point in this vast, it's n characters, but if I got anywhere there, I'd have to have a CC over here. And that's what they explain here. They use a simple example of n equals 6. But, the n's could be... really, they're not specifying any n's right now, so this could be huge. But here are some possibilities. So these ones count, but these ones don't, because here's an AB or a BA, and you don't see a CC to the other side. And this one here has no CCs. Neither does this one. Okay, and there is a question buried in here. Prove that f of 2097, not a nice number as far as I'm aware, is a multiple of 97. Well, one is 2,000 more than the other, but I highly doubt that there's some sort of nice recurrence relation with f like that. How best to approach this? Oop. Got a driver available. That's gone now. Anyway, what to do? So the fact that 2097 is kind of awkward. So is 97. It's a prime number, but it is not a prime number that comes up very often on contests. And they told me it's FN. I think if they were just interested in 2097 on its own, they might have said, consider strings of length 2097. Let capital N be the number that do this. So I feel like them talking about this FN might be a little bit of a hint to maybe work out a formula for FN. I don't know if that's doable, but we can try it. No reason not to, right? But I think that might be something to try. CC occurs as a substring. And then we got to watch out for these ABs. there definitely has to be a CC. So let's be general. So let us try to find a formula for Fn. Okay, so imagine I've got n things. Now I know I have to have a CC somewhere. Oh, maybe we could have tried... I mean, I was sort of placing my C's. I guess we could have said, where's the first CC in B part? That might have been faster. Maybe that's what we were intended to do. Because now I'm tempted to say, well, let's pick where the first CC occurs. And we don't care what happens after it. We do want to make sure, because this has to be the first CC, that there are no CCs beforehand, but also that there are no BAs, because that would force another CC to have to occur. So you can start your CC anywhere but the last one. So there are n-1 places to start the first appearance. And you could say read left to right. I think it would be obvious to whoever's marking. Of CC. Okay. So let's say, well, we'll do it on the next page. So there's n of them. So suppose my CC occurs here. So we'll start it at, I don't know, position P. So this would be P plus 1. How many things are left? So there's n of them minus P minus 1, right? Because this is 1, 2, 3, 4, 5. So in our example, I've got 6, I've got 7, 8, 9, 10. There's 10 minus 7, yeah, so there's 3 of them. N minus P minus 1 letters. That can be chosen in any way. So that would be, we don't care what those letters are. So, I mean, they could all be C's, they could all be A's, they could be some combination of A's, B's, C's, doesn't matter. So there's 3 to the n minus P minus 1 choices. All right, and then there's P minus 1 things to choose here. But we need no CCs, no ABs, and no BAs. Now I like that there's sort of there's the same number of C's, A's, and B's being represented here. I would almost call it symmetric, except it's not exactly symmetric. So what can we do? I want to count this. I want this to be nice and simple, like 7 or something. I want it to be a number. Obviously, it would depend on P. So, not 3 to the P minus 1, but maybe something similar. Like, I don't know, 7 times 2 to the P minus 1, similar to what we saw a little while ago. So we could maybe try to do what we did in B part and count the number of strings, in this case strings of length P minus 1, that don't contain an AB or a BA. I mean, we were fine doing that when it came to counting the number that don't contain a CC, so that's certainly possible. So I need them not to contain CCs, not to contain ABs, and not to contain BAs. However, we're also going to have to make sure that whatever we do does not end up ending with a C, because then I'd have an earlier occurrence of CC. So we've got to be careful. So I can't have a C there. Now it could end in an A or a B, doesn't really matter what. If it ends with an A or a B, I couldn't have it preceded by a B or A respectively. Huh. Let's, Okay. So the string of length p minus 1 cannot end in a C. Otherwise, we get an earlier CC. There's my CC. This can't be a C. It could be an A. Now, if it's an A, this can't be a B, because then I'd have a BA, and I'm not allowed to have BA before this first CC. But it could be an A or a C. Anytime I do a C, I can't have another C ahead of it. So I have to have an A or a B. Anytime I have an A, I can't have a B ahead of it. So I'd have to have an A or a C. Right? So here's what I want to say. Let us build a string backwards. Anytime we have a C, we cannot have C before it, only A or B. So anytime I see a C, I have two choices for what could be before it. If we have an A, it cannot have a B before it. But it could go back to an A or a C. And same thing with B. Okay, B can't have the A before it, but it could have the other two. Yeah, so kind of is symmetric in a sense. So what's my language? If we have, I'll switch it up. I'll say if we place a C or a B. We can't put an A before it. Only a C or a B. Each letter we add gives two choices for the letter before. So if I imagine, here's my CC, I've got P minus 1 things. I've got two choices for what I can have here, an A or a B. Now, depending on which one it is, I then have two choices for what can go here, two choices for here, two choices for here. Now, what is available here depends on what came before it, but it's always two choices. So there should be 2 to the P minus 1 ways to fill. We could call this the prefix of our CC, and then the other part is the suffix. So, for the first CC, first appearing at position P, there are 2 to the P minus 1, and then it was 3 n to the minus P minus 1? N minus P minus 1. So the total, this isn't going to be the nicest thing, but so So P can be, you could have the first, you can have anything but the last position. So this will be the sum of 2 to the 1 minus 1, 3 to the n minus 2, and 2 to the... So this one will increase by 1. This one will decrease by 1 each time. So 3 to the n minus 3, 2 to the 2, 3 to the n minus 4. How's it going to end? N minus 2 here, and 3 to the... So if P is n minus 1, n minus n minus 1 will just be 1, minus a 1 will be 0. Oh, so the top always adds up to n minus 2. Those two exponents. Okay. This looks nice and regular enough. I'm just going to write a little bit more of the sequence. Can I find a way to... So every time you go over, you multiply by 2 but divide by 3. Oh, this is a geometric sequence. Or a geometric series because we're adding them up. So there's a geometric series with A being 3 to the n minus 2, that first term we've got. And R, what do you multiply each term by to get the next term? You multiply by 2, divide by 3, so you multiply by 2/3. And how many terms are there? So this would be... So Fn is 3 to the n minus 2 plus 3 to the n minus 2 times 2/3 plus 3 to the n minus 2 times 2/3 squared, plus 3 to the n minus 2 times 2/3 to the n minus 2. That completely cancels out all the 3's, leaving with 3 to the 0, and leaves us with 2 to the n minus 2 on top. All right, now there's a formula to add up geometric series. If you go to, well, we won't use n, usually you use n, let's say k minus 1. The formula is it's a r to the k minus 1 all over r minus 1. Right, so I guess we can simplify Fn to be 3 to the n minus 2, 2 over 3 to the n minus 1, increase by 1, minus 1, all over 2/3 minus 1. Oh boy, okay, we can simplify this, I'm sure. 3 to the n minus 2, we'll say 2 to the n minus 1 over 3 to the n minus 1 minus 3 to the n minus 1 over 3 to the n minus 1, all over 2 over 3 minus 3 over 3. To the n minus 2, it'll be a negative 1 over 3 on the bottom. 2 to the n minus 1 minus 3 to the n minus 1 on top. And then, what shall we have? 3 to the n minus 2 here. Well, I guess this can cancel out with almost all of this. And then the minus 1 is going to allow me to flip the signs. So I'll have 3 to the n minus 1 minus 2 to the n minus 1 divided by 3, and then to divide by 1/3 you invert and multiply, so there the final 3's will cancel. 3 to the n minus 1 minus 2 to the n minus 1. So that is a very, very nice looking formula. But of course, I'm assuming my analysis is correct. Now, it didn't seem incorrect, so I'm quite happy with it. A nice, clean-looking answer. But if we wanted to, we could double-check this, couldn't we? We could, work out how many strings work with length 4 and just make sure that it really is that f of 4 is 27 minus 8, so 19. That wouldn't be that hard to work out, right? We could quickly double-check that. Or, actually, we could make it even simpler. F of 3 would be 9 minus 4, right? So it should be 5. So can I think of... five strings that do this? So there's the C's all in front. And we have C's here. Yeah, there we go. So that seemed to work. I mean, if you want more convincing, try f of 4. But I'm happy with the formula. It looks nice and neat. And now I know what Fn is, period. Okay, so that's kind of cool. I wonder if we could change... this is just me thinking. I wonder if we had a D. You could have A, B, C, and D. If that would change this to a 4 to the n minus 1, and then some way to get a 3 to the n minus 1 if also any DDs must be preceded by CCs. Just things I'm thinking about. I always like when I do these questions to think, how could I take this and turn it into another question that maybe builds upon it, maybe it's a little simpler. Anyway, that's for me to think about after I'm done recording. All right, what was it? It was 2097 is a multiple of 97. Okay, well, 2097 going to be 3 to the 2097 minus 2 to the 2097. And that is way too big for my calculator. So I couldn't just compute this and ask, are you divisible by 97? So there's got to be some sort of trick to this. Oh, wait, no, it's minus 1. 2096 minus 2 to the 2096. Well, one thing we can do, could rewrite this as 3 minus 2, 3 to the 2095, plus 3 to the 2094 times 2 plus... There are ways to factor this. I'm just not sure I like any of them. And I mean, that's kind of meaningless as well because this is a 1, but... there are other ways to factor it. For example, x to the 6 minus y to the 6 can be written as x minus y, x to the 5, x to the 4y, x to the 3y squared, x to the 2y cubed, x, y to the 4, y to the 5. But it doesn't have to be written like that. It could be, you could take out x cubed minus y cubed and x cubed plus y cubed. That works. Or you can write it as, there's lots of different ways to do this. X squared minus y squared. You get x to the 4, so it'll go down by x to the 2 each time. And up by y to the 2 each time. So there's lots of ways to write these out. Depending on what we want to do. Do we want to visualize this as x to the 6 minus y to the 6? Or are we secretly viewing this as x to the 3 squared minus y to the 3 squared? Because then I've just done difference of squares here. Do I want to do difference of squares here as well? I mean, 2096 definitely is a square, so we could do difference of squares. Well, difference of squares. If we're going to do that, I mean, the goal here is I'm trying to get 97. If I could get an x minus y or an x cubed minus y cubed to be 97, that would be great. and they have to be powers of 3 and 2. So maybe the next thing we should do is take a look at some simple powers of 3 and powers of 2 and see, can I add them or subtract them to maybe get 97. Yeah, 97. 97's, I mean, it's close to 81, but you know, we can just be a bit more methodical about this. So let's say we'll call it K. Talk about 3 to the K, 2 to the K, and now if I add them or if I subtract. Actually, we'll do the subtract one first. Just because it's a lot easier, I think, to pull out a subtraction. Notice how I pulled out subtractions here. It's only this one that I got a sum of squares, and maybe we're needing to look for something like this that's a bit more complicated. That's possible. With 1, I'll get 3, 2, difference is 1, that was not helpful, and 5, but that's okay. So 9, 4, difference is 5, sum is 13. 27, 8, so difference is 19, sum is 35, so we're not really getting close to 97 here. 81, now 81's pretty close. And the next power of 3 would be 243, so I think that's a little too big, but it's wishful thinking right here. So 16, 81 minus 16, obviously subtracting it isn't going to do me any good, but 65. Adding them, however, there it is, 97. So, what do I need to do? I need to get 3 to the 4 plus 2 to the 4. Now, here's where we hope. 2096, just grab a calculator. 2096, does it divide by 8? It does. Okay, good. Otherwise, I would have had a very big problem. Because I can't just go and pull any of these out. Like, the 5s I actually couldn't do because 2096 isn't a multiple of 5. So with all these x to the 6s and y to the 6s, you're never going to pull out x to the 4 minus y to the 4. It just doesn't work. They have to be factors. Okay? Anyway, so F 2097 is 3 to the 2096 minus 2 to the 2096, which I will factor as 3 to the 8 minus 2 to the 8, but now this is a difference of squares. We'll say this is 3 to the something. So we'll have 262 terms, but it'll be 2088 plus, I'm just going to subtract by 8 each time. 3 to the 2080, 2 to the 8 plus, and it'll go all the way down to 3 to the 8, 2 to the 2080, 2 to the 2088. Right? And then that part's done. Who cares about that? But now I can difference of squares this. So 3 to the 4 minus 2 to the 4. 3 to the 4 plus 2 to the 4. And I'm not going to bother writing it, so I'll use the universal symbol of copy what I just wrote down. I mean, it's a little bit bad form. You probably want to write it all out. But my point is, here is 97. So 97 divides f of 2097. And that's what we were asked to show. All right. So, you know, I didn't find that one too bad. I like counting questions. I like combinatorial questions. What this is. If this had been a 3D geometry question, as I've stated in the past, those are some of my least favorites to do. Or something that has a surprising number of cases. I didn't find too many cases here. Although I think maybe I could have done B part faster if I had decided to pick where the first CC is. I sort of stumbled across that picking where the first C was, but I think I could have done it a little faster. And that would have had a nicer connection into what we did with C part. Okay, but there we go. That finishes off our 2018 CIMC paper. Sorry, it's not CIMC, CSMC. I was about to mention, if you found this difficult, you want to look for something a little easier, you can take a look at the CIMC, the Canadian Intermediate. It's aimed at a grade level less. I've got a bunch of other Canadian senior papers out there, other difficult contests in the same vein. Canadian Open I go through. The Euclid contest, also put out by Waterloo, also aimed at about the same level. It's got one extra question, but yeah, it's good. So if you're looking for just more B3 practice, look at any of my senior papers, or Euclid 10s are also similar, I would say, in difficulty. But that's it for me. Thank you guys so much for watching. Feel free to like or subscribe, or if you have different ways of doing the questions, by all means, write them down below. I'm always keen to read those. But I'm going to go take a break and think about ways I could modify this question. Have a wonderful day.